Lecture 15. I think this is the last lecture on differential equations. And we are going to continue with Laplace transforms. And so we did already shift formula 1, which I will recall, which says that Laplace transform of e to the at ft, if you multiply the function by e to the at and pass it through the box, meaning I'm thinking of L as a box, you multiply f by e to the at, and then what comes out is LF evaluated at s minus a. And so we saw last time how to use this to find the inverse transform of a given function, particularly when the function is a ratio of two polynomials and the denominator doesn't factor. So let me do one example before we go further. So find f given that LF is 4s minus 1 over s square minus 6s plus 10. So again, here you see that your denominator doesn't factor. So I want to find f, which is L inverse 4s minus 1 over s square minus 6s plus 10. So you want to complete squares. So since, let me just write this remark, since the denominator does not factor, complete the squares, complete the square and use shift formula 1. If it factors, then you will use partial fraction. So this I will write as L inverse of 4s minus 1 over s minus 3 square. That should give you s square minus 6s plus 9. What's left is 1. And then because you have s minus 3 in the denominator, you want to have s minus 3 on the top. So 4 times s minus 3 over s minus 3 square plus 1. That would give you 4s minus 12. You want minus 1, so you have to add 11. And then you just split this in two terms. First is 4 times s minus 3 over s minus 3 square plus 1 plus L inverse of 11 over s minus 3 square plus 1. And now the rest is easy. 4 comes out. And this is just the inverse. If this 3 is not there, s minus 3, if it is replaced by s, then it is the Laplace transform of cos t. But that's shifted by 3. Similarly, the second term is the Laplace transform of sine t shifted by 3. So the inverse transform of this will be e to the 3t cos t, and the inverse transform of that will be e to the 3t sine t. So this is the way you use shift formula 1 to find the inverse transforms. In doing so, you have to use the completing square trick. So now I will talk about shift formula 2. So first of all, I will define a function u sub a, which is given by u sub a is, so for a positive, let us define a function u sub a to be 1 if t is between 0 and a, and it's 0 after a. No, I'm sorry, I made a mistake. This is not u sub a. So let me start with u sub a is 1 after a and is 0 before a. So definition: for a positive, define a function u sub a of t to be 0 if t is less than or equal to a, and is 1 if t is greater, t is less than a, and then one if t is bigger than or equal to a. So this is like, as I told you, that this technique of Laplace transform is going to be used in circuits with switches. So this is as if you have a switch which is turned on at time a and then it is held on forever. So this is the picture, this is the graph of UA. Now I'm going to consider the function. So let f be a function given to you, f be the function on 0 infinity to r. What you want to, suppose, let me draw the graph of f. It's something like this. Then you have learned in calculus, in calc 1 or even in pre-calc, that the function f of t minus a is exactly, the graph of this is the graph of f pushed to the right by the amount a, because whatever is happening at a will happen at 0, or whatever was happening at 0 for f will happen at a. So this function would be something like that. The graph of this function would be that. Now to make it more formal, have something between 0 and a, what I do is I look at the function f of t minus a times ua. So this function has a graph which is 0 till a, and then after a, u will be 1, and so then it will be the graph of f. So this function, which is given a function f, in terms of graph of f, you take a function whose graph is obtained from the graph of f by pulling the graph of f to the right by amount a and making the function 0 between 0 to a, and then you take that function f, and that function is f of t minus a ua. So the shift formula 2 is going to tell you something about the Laplace transform of this function. So let me write down shift formula 2. Laplace transform of f of t minus a ua is given by e to the minus as times Laplace transform of f. So in other words, if you think of f of t minus a ua as a shift of f, then shift of f pass through the box. So let me draw the picture of this. Here it is f shifted. What comes out is multiply L of f by exponential, by e to the minus s. This is shift formula 2. This is the box L. And shift formula 1 says that if you multiply f before passing through the box by e to the at, then what goes out is the shift of f by the amount a. So these are sort of opposites of each other. And now I will give you a proof of this first, and then we will see how to use this. Okay, so the proof is not difficult. Proof, let's just calculate what the left hand side is. So it is L of f of t minus a u sub a at s. By definition, this is integral 0 to infinity e to the minus st f of t minus a u sub a t dt. So this is going to be this will be simply integral a to infinity, because still a, u is going to make this whole thing 0. So it's minus a minus st f of t minus a dt, which you will write as a limit, of course, m tends to infinity, a to m e to the minus st f of t minus a dt. And now you put a variable u equal to, you make the change of variable u equal to t minus a, so du equals dt. And then when u is a, when t is a, u is 0. When t is m, u is m minus a. So therefore we get limit as m tends to infinity integral 0 to m minus a e to the minus s, and now you see t minus a is u. So t will be a plus a plus u or u plus a times f of u, dt is du. So this is limit m tends to infinity 0 to m minus a e to the minus su f of u du, and then there is a factor of e to the minus as left, which has nothing to do with the limit, because the limit is when m tends to infinity. Now as m tends to infinity, m minus a also tends to infinity. So the left hand limit, this limit, not the left hand limit, this limit is same as, I can write this as limit as m minus a tends to infinity, integral 0 to m minus a e to the minus su f of u du times e to the minus s. But then this limit is just the Laplace transform of f. So I will write this as e to the minus s Laplace transform of f. So that's the proof. So the proof is complete. Now we are going to see how to use this formula to first of all find Laplace transforms of discontinuous functions and then find the inverse transforms. So problems, so examples, let's start. We begin first of all by applying, let's look at just Laplace transform of u sub a. So what is u sub a? Here the function f is, so here this is where f is 1. So I can take the function 1, take ft to be constant function 1. So this is f of t minus a ua, because f of t minus a is same as f of t, 1 of t minus a is same as 1 of t, which is just 1. So this by the formula is going to be e to the minus s times Laplace transform of 1. And Laplace transform of 1 is 1 over s. So we get this important formula that Laplace transform of u sub a is e to the minus s by s. This should be added to your table of formulae. And we will learn one more important thing which we will keep in mind, and that is example 2. If you look at a function, suppose you have 2 points a and b, a is less than b, and I look at a so-called bump function which is 1 between a and b and 0 outside. Note that this function called bump function on interval AB given by shall we call this b of t. B of t is given to be 0 if t is less than a, 1 if t is between a and b, and 0 if t is bigger than b, after b. So note that this bump function is nothing but ua minus ub. Because ua will be 0, ub will be 0, so for t is less than a, ua minus ub is 0 minus 0, so is 0. Between t in between a and b, ua is 1, ub is 0, so this difference is 1. and after b both are 1, so the difference is 0. So the bump function is always ua minus ub. So the Laplace transform of a bump function is going to be e to the minus as by s minus e to the minus bs by s. It's Laplace transform of ua minus Laplace transform of ub. Given that, now we can find out some Laplace transforms of some functions, which I will describe by graphs. Example 3. Let's take a function ft which is given by say bump between 0 to 1. I mean, from 0 to 1 it is 0. Between 1 to 3 it is 1. Then it is 0 between 3 to 4. And then 1 onwards after 4. So that's the graph of my function. F is as shown in the graph. Find LF. So first you have to write this f in terms of these bump functions. So note that. So you first write f in terms of u sub a's. So you will see that the bump between 1 and 3 will amount to the function u1 minus u3. That will give you the function which will give you a bump which is 1 between 1 and 3 and 0 everywhere. Then you have to add a u4 because you want everything to be 1 after 4. So this is your function, and so LF of this will be e to the minus s by s minus e to the minus 3s by s plus e to the 4s by s, because Laplace transform of e to the ua is e to the minus as by s. So this is okay. Now let's do something like this. So example 4. Let's take the function whose graph is like this. So this is the point 1. Let ft be as shown. Find del of f. So now first thing is you will have to find the equation for this line. The equation for this line is very easy. Notice that this line is going to be, let me call the x variable t, then this line is y of t, y equals t, isn't it? This is the angle bisector, so this is the line y equals t. So our function is going to be, ft is going to be t times, now I want to make a bump function here between 0 and 1, so it is u1 minus u0. That will give you 1 between 0 and 1, so you are multiplying it by t. And then after that, so if you look at just this function, it will be t between 0 and 1, and then everything is 0. You want to add 1 to that, so you will add u1 to this. Good. So that's going to be your function. So then we want to take, which you can simplify and write as t plus 1 u1 minus t u0. Good. And now I want to take LF, which is going to be L of t plus 1 u1 minus L of t u0. Now let me recall what is the formula. The formula says that Laplace transform of f at t minus a ua is equal to e to the minus as Laplace transform of f. So evaluating this is easier because this is already t minus 0, but here you have t plus 1. So, and your a is 1. So you may want to write down, not may, you have to write this as t minus 1 plus 1 plus 2, because the reason for that is you will not be able to apply this formula because your a has to be 1. In order to apply this formula, your f must be of the form f of t minus a, and here it is t plus 1. it should be t minus 1. So I want to write it like this and then split this in two terms, t minus a u1 plus 2 u1. This is quite easy. This is L of t minus 0 u0. And so this Laplace transform by the formula will be a is 0. So it is e to the s, which is e to the 1, e to the minus s, which is e to the minus 0 s, times Laplace transform of t. So continuing this, you will get the last term is going to be just 1, and Laplace transform of t is 1 over s square. Good. Here you split this in two terms, L of t minus 1 u1 plus 2L of u1. 2 is a scalar which comes out, and this is by the formula, this is going to be e to the minus at, a is 1, this is u, it doesn't look like u. So this is e to the minus t times Laplace transform of t. This will be 2 e to the minus t by s, and this will be minus 1 over s square. And Laplace transform of t is 1 over s square. So this is e to the minus t by s square plus 2 e to the minus t by s, minus 1 by s square. So if you have a slanting curve, you have to first find its equation. I mean, this is a slanting, meaning by that I mean, unlike the first three examples, you have a curve, or it's not a curve, it's a straight line, but it is with some slope. It is not parallel to x-axis. So, like in the first three examples. So this is what you need to do. Let's do one more. Example, what number is this? Example 5. Good. So let's take, so now I'm going to draw the graph and this is the graph of f. Find the Laplace transform of this. Find the Laplace transform of f. So again, we will have to write down the equation of this line. And so what will that be? So equation of the line, I will recall. Equation of the line, this is from your pre-calc, with slope m and passing through a comma b is y minus b equal to m times x minus a. So I want to find first of all the equation. So first find the equation of this line. Equation of the, what should I say? Equation of the line in the definition of f, in the function f, in the graph of the function f. So here you see that the slope of this is, its slope is going to be, so you know it passes through, maybe I'll write it more systematically. It passes through, to find its slope you need to take 2 points, 0, 2 and 1, 1. And I take y2 minus y1, y2 minus y1 over x2 minus x1. And so slope is minus half. And so its equation is going to be, I call my x variable t. So the equation is going to be y minus 2 or y minus 0 equal to the slope times x minus or t minus 1, t minus 2. This point I am taking as my point a comma b. So the equation of this line is y equal to minus half t minus 2. So now we can write down what the function is. So f of t, hence the given f is, so first of all you want to have a bump between 0 to 1, so that's going to be u0 minus u1. That gives you this function, 1 between 0 and 1, 0 afterwards. And then to that I want to add, I take this function minus half t minus 2, that's that line, and put a bump between 1 and 2. So it will be u1 minus u2 multiplying this. So that gives you 1 when t is between 1 to 2, 0 afterwards. So that's the formula for your function. So this is going to be u0. Let's collect u0, u1, u2 separately. Let's bring this together. So I have minus u1 minus half t minus 2 u1 and minus half t minus 2 u2. So if you simplify this a little bit, what will you get? You get u0. If you take u1 out common, then you will get, let's try doing this. How should I do this? So I pull out a minus sign, you get minus 1, minus becomes plus now, t by 2, and you get, so you want to have minus t, right? Minus half t, and then you want to have plus 1. So I will put minus 1 here. u1, isn't that right? So I get, when I multiply, I get minus u1. I get minus t by 2 u1, and then this product is plus u1, isn't it? I want to have plus u1, so this is minus 1 minus half t minus 2 u2. Good. So this becomes u0, 1 and minus 1 cancel, minus t by 2 u1 minus half t minus 2 u2. Now I take the Laplace transform of f. So this is L of u0 minus half, we can move out, L of t u1 minus half you move out, L of t minus 2 u2. Now you want to apply the formula. So this is going to be e to the minus s by s, right? Sorry, e to the minus as by s. A is 0. So this is going to be just 1 over s. Second term is a tricky one. Third term, let me do this first, because here you see, recall the formula. The formula is Laplace transform of f at t minus a ua. Formula says something about this. So I have here ft equal to t. So, and a is 2. So this is f evaluated at t minus 2. So I can write this immediately as e to the minus 2s Laplace transform of t. For this middle term, you have to work a little bit more, because the middle term does not have f at t minus a. A is 1. So you have to write the middle term as t minus 1 plus 1 u1. And you will split it in two terms. So this is the trick you have to be aware of. So this is minus half into parenthesis. I will get L of t minus 1 u1 plus L of u1. And let me erase this. Minus e to the minus 2s Laplace transform of t is s1 over s square. And so this becomes, here your function is t. So this is e to the minus s Laplace transform of t plus Laplace transform of u1 is e to the minus s by s, e to the minus 2s by s square. And so the answer will be e to the minus s Laplace transform of t is 1 over s square plus e to the minus s by s minus e to the minus 2s by s square. So this is the trick that you have to keep in mind, which happened also on the previous problem, because here we wanted to write here you wanted to write tu1 as, no, that's on this problem. You want to write tu1 as t minus 1 plus 1 u1. And so this is the thing to watch. And that happened in the previous problem, didn't it? Didn't it happen? Yes, I think here we had t plus 1 u1, which you write as t minus 1. Here again, I will put here again there and here again here. So this is the trick you should be careful about when you apply this formula. So you will need practice for doing these chores, but it's not difficult. Now we'll see how to use this shift formula 2 to find the inverses. So now we shall see how to use shift formula 2 to find L inverse. So the first thing that you should note is that L of f t minus a ua is e to the minus as times Laplace transform of f. So you have to have this factor e to the minus as. That tells you that you will need to use shift formula 2. So whenever you see a term e to the minus as in the expression for Ls, L of f s, then you know to find f we need to use shift formula 2. So let me do this with examples. So example, let's take LF to be LF of s be e to the minus 2s by s minus e to the minus 4s by s. Find f. So the idea is simple. You ignore the exponential factor, find the inverse transform of the remaining. So since L inverse of 1 over s you know is 1, isn't it? L of 1 is 1 over s. So therefore L inverse of 2 to the minus s 1 by s, or I can use I'm making it too complicated. Here you don't have to do that, because you should remember the formula. L of ua is e to the minus as by s. So this problem is much more direct. So I will just write down the answer directly, as it's going to be ua u1 u2 minus u4. That's going to be your function, which is the bump function between 2 and 4. So this function is 1 between 2 and 4 and is 0 everywhere else. That's your f. Example 1. Example 2. Let's do this one. LF of s is e to the minus 2s by s square. Now what I was telling you there, you should do that here. That is, first find L inverse of 1 over s square without the exponential term. This you know is t. Therefore, by the shift formula 2, by shift 2, L inverse of e to the minus 2s by s square will be f at t minus a times ua. Right? The formula says what? Formula says that L inverse of e to the minus s by times LF is f at t minus a ua. So here your f is t, because f of t is 1 over s square. So, but this is t evaluated at this function ft is equal to t. It's evaluated not at t but t minus 2. So this is going to be, so this will be f at t minus 2 u2. What is f? F is just your t minus, f of t is t. So this is t minus 2 u2 is the answer. Good. So I've written it a bit sloppily, but let me do one more and then I will write it more properly. So let's find f given that LF of s is e to the minus 2s over s square plus 3s plus 2. So again, you ignore the exponential factor and you find out the function whose Laplace transform is the remaining. So first find L inverse of 1 over s square plus 3s plus 2. This will give you f. This we will call f. Then the inverse transform of e to the minus 2s over s square plus 3s plus 2 will be simply this f evaluated at not at t but t minus 2, because you have a 2 here, times u2. So let's first find out L inverse of 1 over s square plus 2s plus 2, 3s plus 2. This one factors nicely. So it's going to be based on partial fractions. Good. I think these partial fractions are easy, isn't it? 1 over s plus 2 times 1 times s plus 1. This I can simply write as 1 over s plus 1 minus 1 over s plus 2, because the difference of these two is 1. So therefore L inverse of 1 over s plus 2 times s plus 1 is L inverse of 1 over s plus 1 minus L inverse of 1 over s plus 2, which is e to the minus t minus e to the minus 2t. Good, that's your f. So therefore L inverse of e to the minus 2t over s plus 1, or whatever we had, s square plus 3s plus 2, equals this function f at t minus 2 u2. And so this will be e to the minus of t minus 2. Instead of t you put t minus 2. E to the minus 2t, but instead of t I put t minus 2. And then this whole thing is multiplied by u2. So that's your function whose Laplace transform is the given function. So one more example. Let's do one where we have to use shift formula 1 to find the inverse of the term without the exponential. So let's say find f given that LF of s is, say, e to the minus 3s over s square plus 4s plus, say to get nice numbers I should add nice number, so make it 13. So here you cannot find the factor the denominator. So first find L inverse of s square plus 4s plus 13. So here the denominator does not factor. So whenever the denominator doesn't factor, you have to use completing squares, trick of completing squares and shift formula 1. So we use the trick of completing squares and shift 1. So we know how to do that. 1 over, this will be written as s square plus 4s plus 4 plus 9, because this is a perfect square. That's the underlying idea. So this is L inverse of 1 over s plus 2 square plus 3 square. So you see, without the plus 2, this would be 1 over s square plus 3 square. That should hint at looking at sine of 3t, but sine of 3t's Laplace transform will give you 3 on the top, which I don't have. So I put 3 on the top. And then you have to divide by that 3, which I take outside. And then this will be the inverse transform of this will be, see, without the 2, inverse transform is sine of 3t. But because of the shift by minus 2, recall your shift formula 1. This will be e to the, see, Laplace transform of e to the at, and recall shift formula 1 is Laplace transform of e to the at f t is going to be lf at s minus a. Your a is minus 2, so this is going to be e to the minus 2t sine 3t. So now we go back, this we will call f, and then now L inverse of, I had a factor of e to the minus 3t on the top, isn't it? Yeah, minus 3s divided by s square plus 4s plus 13. This will be, by here I am using shift formula 2. This will be f at t minus 3, because you have a 3 here, times u3. And so this is going to be where f is your function given by this. So this final answer is going to be 1/3 e to the minus 2, t is replaced by t minus 3, sine of 3, t minus 3, u3. So that's how you apply shift formula 2. And now you need practice. So let's now do some differential equations with discontinuous right hand side, where all of this is put together. Good. So let's see example. Solve the IVP using Laplace transforms. And the problem is, say, let's take y double prime minus 3y prime plus 2y equal to, and I write this function ft whose graph is given. So I'll take a simple situation first. It's a bump between 1 and 3. That's my function f. So this is like turning on the switch at time 1 and turning it off at time 3. That's your electric circuit with right hand side. I can multiply it by some function, but let's not make it too complicated to begin with. And your initial conditions are y at 0 is 1, y prime 0 is 0. So we have this problem. See, this is where we will need the techniques of Laplace transform and not our previous ways of solving constant coefficient systems. So we begin by first write down f in terms of, first write down f in terms of ua's. So note that your f is u1 minus u3. So therefore our equation is y double prime minus 3y prime plus 2y equal to u1 minus u3. Now you take L of both sides as before. So I get L of y double prime minus 3y prime plus 2y, that must be L of u1 minus u3. So now write down what the left hand side is. So it is Ly double prime minus 3Ly prime plus 2Ly, good, equal to Lu1 minus Lu3. and Ly double prime is s square Ly minus sy0 minus y prime 0 minus 3 times Ly prime is s Ly minus y0 plus 2Ly, and that should be L of u1 is e to the minus s by s, s of u3 is e to the minus 3s by s. So let's simplify this. So what do we get? So you collect terms in Ly. So you get s square minus 3s plus 2Ly. Then you have sy0, y0 is 1, y prime 0 is 0, and then you have this term which is plus 3, y0 is 1, so it is plus 3, and that should be equal to e to the minus s by s minus e to the minus 3s by s. So now you just solve. This is an algebraic equation in Ly. So I move this 3 and s on the right side. So maybe I will take one more step to write this. So I get s square minus 3s plus 2 Ly equal to s minus 3 plus e to the minus s by s minus e to the minus 2s by s. So therefore, Ly is going to be, I will divide the right hand side by this, s square minus 3s plus 2, s minus 3 by that, plus e to the minus s over s times s square minus 3s plus 2 minus e to the minus 3s over s times s square minus 3s plus 2. Now this is going to test everything that we have done so far, reading of the inverse transform. So y, our solution will be L inverse of s minus 3. Now this denominator here factors, so we can write the factors as s minus 1 times s minus 2 plus L inverse of e to the minus s over s square minus s minus 1 times s minus 2 minus e to the minus L inverse of e to the minus s over s times s minus 1 times s minus 2. So now first of all we'll need to calculate this separately. So first consider partial fractions of s minus 3 over s minus 1 times s minus 2. Then we'll have to calculate the inverse transform of the other terms without the exponential factor. That's going to take some time, but let's do this. So this is a divided by s minus 1 plus b divided by s minus 2. So s minus 3 will be a times s minus 2 plus b times s minus 1. So coefficients of s to the 1 is 1 on the left side and is a plus b on the right. Coefficient of s to the 0 is minus 3, which is minus 2a minus b. So if I add them, I get minus a equal to minus 2. So a will be 2 and then b has to be 1 because a plus b is 1. Yeah. This is plus 2, right? No, this is minus. Have I done this right? Let me just double check. I'm adding these two. One sec. Let's not make a mistake in calculation. So this is going to be minus 3 was minus 2a minus b. So I added this, so I get minus a equal to minus 2. So a equal to 2 and a plus b is 1, so b is minus 1 and not 1. Good, then this will be satisfied. Yes. Okay, so good. So therefore L inverse of s minus 3 over s minus 1 times s minus 2 is simply L inverse of 2 over s minus 1 minus L inverse of b is minus 1, so it's that, and so this is 2 e to the t minus e to the 2t. That's the L inverse of the first term. Now we want first L inverse of, I want to ignore the exponential terms and I want to find the inverse of s times s minus 1 times s minus 2. Good. Now you use the fact that you have a factor of 1 over s. That means if you know the inverse transform of the remaining thing, then you integrate that to get the inverse transform of this function. So first we find L inverse of 1 over s minus 1 times 1 over s minus 2. Its partial fractions are easy to write down. We don't need to go through the a and b stuff because this term is simply, you can see it's going to be s minus 2 minus 1 over s minus 1, because if I subtract s minus 1 minus s minus 2 I get 1 on the top. So this partial fractioning is easy. So this is just going to be e to the 2t minus e to the t. Good. So therefore L inverse of 1 over s times s minus 1 times s minus 2 will be the integral of this thing, and so this is because of our integration formula. Laplace transform of the integral of f is 1 over s times Laplace transform of f. So this is e to the 2t by 2 minus e to the t evaluated between 0 to t, which gives you e to the 2t by 2 minus e to the t minus, the value at 0 here is 1/2 minus 1. So this will be e to the 2t by 2 minus e to the t. This is minus half, and then the minus outside will give you plus half. So now you need Laplace transform of e to the minus s over this term. So therefore Laplace transform of, or the inverse transform of e to the minus, what did we have? E to the minus s and e to the minus 3s. So that's not going to be difficult. So e to the minus s over s times s minus 1 times s minus 2. By shift formula 2, you know that the function f, whose Laplace transform is 1 over s times s minus 1 times s minus 2, is given here. So this function has to be evaluated at, now your a is 1. Remember the formula, Laplace transform of f of t minus a ua is e to the minus as Laplace transform of f. So here a is 1. So this function has to be evaluated at, not at t but t minus 1, and multiplied by u1, and L inverse of e to the minus 3s over s times s minus 1 times s minus 2 would be the same function evaluated now at, not at t but t minus 3. So e to the 2t minus 3 minus e to the, by 2 I forgot, t minus 3 plus half u3. So what is our answer? So final answer is going to be yt is going to be, now let's go back and see, it's Laplace, it's the sum of the first two and the third one is subtracted. This one we evaluated, where did it go? It is 2e to the t minus e to the 2t. So 2e to the t minus e to the 2t. That was our Laplace transform of the first term, which was this, and then plus this minus that. So plus e to the 2t minus 1 by 2 minus e to the t minus 1 plus a half u1 minus e to the 2t minus 3 by 2 minus e to the t minus 3 plus a half u3. So that's your solution to the IVP. So if you look at this problem carefully, it needs all of the things that we have done before, except it didn't need, because the denominator here factored, it didn't need shift formula 1. So it touched on everything that we have done except shift formula 1. I can give you another one to do where you will need shift formula 2. Yes, I can do that quickly. If I look at the same problem but make the, yeah, let's have another problem. The same, I can give you another problem. So one more example which I will not probably do. I will do this in the class maybe, or in the lectures that we have left. So example is find the, this you should try to do yourself, find the solution to the IVP. I can make it exactly like what we had, but instead of factorizable expression, let me make it something like plus 5y. That will give you something which is not factorizable, and where ft is as before, and let's take the initial conditions also as before. So this is for you to do. Just to check on one more thing about how to find the Laplace transform, let me do one more problem. Let's take the function, let's take for example 0, then it goes from 1 to 2. Sorry, I mean join this point, this is height at height 1, then you make this 1, and then you drop it and make it 0 here onwards. So that's your function f. Find LF. Let's try to do this and then we'll end. So as you see that this function, you will need the equation of this line. So first find the equation of, you shouldn't do it like this, but anyway, of this line. So this point is 1, 0, this point is 2, 1. So you take the slope of this. Slope is difference between y coordinates over difference between x coordinates. So slope is 1 by 1, which is 1. And the equation is y minus b equal to m times x minus a. M is 1. So I will use the point 1, 0. So y minus 0 equal to 1 times x minus 1. X is t now. So your equation is y equal to t minus 1. That's the equation of this line. Good. So now we can write down the function ft as equal to, you want to have a bump between 1 and 2. So you will take u1 minus u2 and multiply it by this function which is t minus 1. Then you want to have another bump between 2 and 3, so which will be u2 minus u3, and then nothing. So that's this function. So let's try now to find LF. So I will collect t minus 1. I will write this in terms of u1, u2, u3. So t minus 1 times u1 minus t minus 1 u2 plus u2 and a minus u3. So this is t minus 1 u1. This sum will give you what? You have t minus t. Then you have plus 1 and 1, so plus 2. So this will give you t minus 2 u2 minus u3. Am I right? So that's good, because we want this shift by minus 2. Otherwise you will have to do the adjustment. So we don't have to do the adjustment here. So now we can write LF very easily. So this is L of t minus 1 u1 minus L of t minus 2u2 minus L of u3. And you know this Laplace transform of f of t minus a ua is e to the minus as by times Laplace transform of f. Here your function is t, whose Laplace transform is 1 over s square. So this will be e to the minus s by s square. This will be e to the minus 2s by s square. And this will be e to the minus 3s by s. So now more practice later in the class, and I think we have covered everything. You need to do more problems. Let me think about what to do about the final exam and so on. I will give you a final breakdown, but you cannot get a grade without doing Laplace transform problems correctly. You cannot skip this, even though it's at the very end. So we'll talk about that and how to have these on the exam and so on. That comes later. So I will stop here and wish you all the best, because this is the last non-synchronized recording. In the class we'll do more problems. So I will